Hey everyone, welcome back for another deep dive. Today we're going to be tackling a topic that's both fascinating and a bit mind-boggling. Prime numbers.
Prime numbers, right.
Yep, we've got some incredible material to dig into, like excerpts from Marcus du Sautoy's The Music of the Primes.
Ah, great book.
It is. And we've also got some biographical info on some of the big names in math who've spent their lives wrestling with these numbers.
Sounds like a plan.
So what we really want to get to the bottom of is, why are these prime numbers so important? And not just in math, but also in things like, cryptography and even quantum physics.
You'd be surprised, how far-reaching these prime numbers really are.
Okay, so before we get too far ahead of ourselves, let's start with the basics. What exactly is a prime number?
A prime number, well, it's a whole number, has to be greater than 1, and here's the catch. It can only be divided evenly by 1 in itself.
So like 2, 3, 5, 7, 11. Those are all prime.
Exactly. Those are your primes. And they're kind of like the building blocks, because every other whole number, you can build it by just multiplying these primes together.
So they're like Lego bricks.
Lego bricks, yeah.
Yeah.
Perfect analogy. You could build all sorts of crazy structures using just those basic pieces.
And just like there's, an almost infinite number of things you can build with Legos, there's also an infinite number of prime numbers.
That's right. Infinite.
Whoa, hold on. Infinite. How do we know that for sure?
Well, Euclid, that ancient Greek mathematician, he proved it over 2,000 years ago. And you know what? His proof is surprisingly elegant. It's a bit much to explain right now, but basically, if you just assume there's like a finite number of primes, you end up with a contradiction.
Oh, I see.
Which means our initial assumption, it has to be wrong. There's got to be an infinite number.
That's really clever. So we've got this infinite set of prime numbers stretching out forever, but they don't seem to follow any predictable pattern, do they?
That's where things get really interesting. The further down the number line you go, prime numbers, they start to thin out.
Really?
It's like they're playing hide and seek, getting harder and harder to find.
Okay, so how do you even begin to predict where these prime numbers are going to pop up?
That's a question that fascinated a guy named Carl Friedrich Gauss.
Gauss, wasn't he like a child prodigy?
Oh, yeah. One of those brilliant mathematicians ever.
I remember reading that he figured out how to add all the numbers from 1 to 100 in his head when he was 7 years old.
You got it.
Yeah.
A true genius.
Hmm.
But even for Gauss, figuring out the primes was a real challenge. You see, he noticed this thinning out of the primes, and he was determined to find a way to predict how they were distributed. He discovered this link between prime numbers and something called logarithms.
Logarithms.
You can think of them as a way to express really big numbers in a more compact way.
Got it.
Gauss's work led to something called the prime number theorem, which tries to predict how often prime numbers appear as you go higher and higher in the number line. Okay, but there were still gaps, mysteries that even Gauss couldn't quite solve.
So who picked up the torch after Gauss?
Well, one of Gauss's students, actually, named Bernhard Riemann, and he took a totally different approach, diving into the world of imaginary numbers.
Imaginary numbers. This sound, imaginary.
They get a bad rap because of their name. But in math, they're just as real and useful as any other number. Think of it as expanding our number system, allowing us to explore stuff that we just couldn't with real numbers alone.
Okay, I'm listening.
So Riemann, he used these imaginary numbers to create a special tool. It's called the zeta function.
The zeta function?
Yeah, you can kind of think of it like a special lens that takes this seemingly random jumble of prime numbers and transforms them into a more ordered pattern.
So he was trying to make sense of the chaos, bring some order to the prime numbers.
Exactly. Imagine a giant landscape with peaks and valleys. That's what Riemann did. He took those prime numbers and transformed them into points at sea level in this landscape. These are what we call the zeros of the zeta function.
Zeros. Got it.
And the location of these zeros, well, it's the key to understanding how accurately we can predict where those prime numbers are going to show up.
So Riemann was like a treasure hunter, mapping out these zeros like buried gold.
You got it. And based on his calculations, he came up with this statement that's become super famous and kind of infamous too, actually. It's called the Riemann Hypothesis.
The Riemann Hypothesis.
You know it. And it's been captivating and puzzling mathematicians for over 150 years.
So what does this hypothesis actually say?
It claims that all of these special zeros, the ones that aren't easily predictable, they're all lined up perfectly along a specific vertical line in this crazy mathematical landscape. Like there's a secret code, a hidden order governing how the primes are spread out.
If that's true, what would that mean for, our understanding of prime numbers? Maybe even for math as a whole.
Well, it would mean there's a really deep connection between prime numbers and randomness itself. If something as chaotic as primes can be described by this elegant, simple rule, then maybe there's a hidden order to all sorts of things we think of as random.
Wow.
And that could change how we see patterns and predictability and everything, from physics to economics to pretty much anything that deals with complex systems.
Okay, that's a lot to unpack.
And we're just getting started.
So Riemann throws down this challenge with his hypothesis. Who are some of the math whizzes who took it on trying to prove or disprove it?
Oh, there have been many.
Okay.
We could start with Hadamard and de la Vallée-Poussin, two mathematicians working, separately back in the late 19th century.
Okay.
They used Riemann's ideas to prove a part of this whole puzzle, what's called the prime number theorem.
So they got close, but didn't quite prove the whole Riemann hypothesis.
Right. They showed that Riemann's ideas were powerful, could unlock some of the secrets of primes, but proving that all those zeros lie on that critical line, like Riemann said, well, that remained out of reach.
Shows how tough this Riemann hypothesis really is.
Exactly.
And then there's G.H. Hardy and J.E. Littlewood, right? They were like, what, the dynamic duo of mathematics in the early 20th century?
Oh, absolutely. They made some major progress actually proving that an infinite number of zeros do lie on that critical line. So at least part of Riemann's hypothesis was confirmed.
Oh.
But they couldn't prove that all the non-trivial zeros lined up perfectly. And get this, along the way they even disproved one of Gauss's conjectures.
Really?
This just goes to show you how complex and sometimes surprising this whole area of mathematics can be.
And what about Srinivasa Ramanujan, that Indian mathematician? I've heard he had this almost mystical intuition for numbers.
His story's amazing. Self-taught genius, rediscovered many of Riemann's findings about the zeta function and primes while working as a clerk in India.
No way.
Limited access to formal math resources,
So this whole thing with prime numbers wasn't just happening in Europe. It was a global effort.
Absolutely. And Ramanujan's work, it really shows how universal math is. His unique insights, they gave a fresh perspective on the Riemann hypothesis. But even with all these brilliant minds working on it, the Riemann hypothesis, it remains unproven.
That's what makes it so interesting, right? This mystery that's lasted for centuries.
It really shows the power of human curiosity and the drive to learn, It seems like every step forward just leads to deeper mysteries, and that's what keeps mathematicians coming back to prime numbers time and time again. Prime numbers, they really are a paradox, aren't they? So simple at first glance, but the deeper you dig, the more complex and mysterious they get.
It's like they're holding on to some fundamental truth about the universe, but they're not quite ready to share it with us.
And here's where things get really wild. In recent years, mathematicians and physicists have started to find this, surprising connection between prime numbers and, get this, quantum physics.
Quantum physics, hold on, that's the world of, subatomic particles and mind-bending theories about reality. How could that possibly be connected to something as straightforward as prime numbers?
I know, right? It's a fairly new area of research, and to be honest, even the experts are still trying to wrap their heads around it. But some physicists believe that the way energy levels are spaced in quantum systems, it might actually be analogous to the spacing of those zeros in Riemann's zeta landscape that we talked about.
So you're suggesting there might be a hidden mathematical structure, like a blueprint, to the quantum world, and somehow prime numbers are part of it.
It's a wild thought, isn't it? It's like finding a secret passage connecting two completely different realms of knowledge. And this is where physicists like Michael Berry and John Keating come in. They were some of the first to see this potential parallel.
Okay, I'm trying to picture this. So is it like saying, the universe is a giant musical instrument and the prime numbers are the musical notes?
The music analogy, that's actually pretty interesting. Think of it this way. Just like musical notes, they can be arranged in these harmonious patterns, right? Well, the way prime numbers are distributed and the spacing of those zeros in the zeta landscape, they might also be governed by some underlying mathematical harmony.
Okay, I kind of see where you're going with this, but how do you even begin to test an idea like that?
Well, Keating and another physicist named Nina Snaith, they developed a formula. This formula, it predicts a specific constant that's related to how those zeros are distributed. It was a bold prediction for sure, but it needed to be confirmed.
And was it?
It was. Two mathematicians, Brian Conry and Steve Gonek, using totally different methods, they independently confirmed Keating and Snaith's prediction. It was a big moment. Suddenly, this seemingly crazy idea that prime numbers might be tied to quantum physics, well, it started to gain some real credibility.
So we've gone from ancient Greek mathematicians thinking about prime numbers to modern physicists exploring the quantum realm. And it sounds like they might actually be converging on some deeper truth.
It just shows you the beauty of scientific inquiry. It's this constant journey of discovery, with each new insight building on what came before. And sometimes, those insights, they come from the most unexpected places.
So up to this point, we've been talking about the theoretical side of prime numbers, but they have these very real practical applications too, right? Especially in the digital age.
Absolutely. Prime numbers are essential to modern cryptography. They're
Right.
the backbone of the RSA algorithm, which is used everywhere, from online transactions to secure communications. It's what keeps our digital world safe.
I know a little bit about how encryption works, but the role of prime numbers has always been a bit of a mystery to me. Can you break it down, in a way that even I can understand?
Sure, the security of RSA, it all boils down to how difficult it is to factor large numbers into their prime components.
So you're saying it's easy to multiply two prime numbers together, get a big number, but going the other way, starting with that big number and figuring out which two primes were multiplied to get it, that's really hard.
You got it. And that difficulty, that's what makes RSA encryption so secure. Even the most powerful computers out there, it would take them ages to crack the code.
I remember reading about this challenge, the RSA 129 challenge, where mathematicians were given this massive number to factor.
Yes. RSA 129. It was a huge deal in the world of cryptography. Back in 1977, they issued this challenge basically to demonstrate how strong the RSA algorithm really was. The number was 129 digits long, practically impossible to factor with the technology they had back then.
So did anyone ever crack it?
It took 17 years, a massive collaborative effort, thousands of computers all working together, and they finally cracked the code in 1994. The whole thing really showed not just the power of prime numbers for securing information, but also how incredibly ingenious mathematicians and computer scientists can be.
So it sounds like this quest to find more efficient ways to factor large numbers, it's this ongoing battle between code makers and code breakers, with prime numbers right at the center.
That's a great way to put it. And the stakes are high. I mean, the security of our entire digital world depends on staying ahead in this cryptographic game.
It really makes you think. This mathematical concept, prime numbers, something that's been around for, what, millennia? And now it's become crucial to our modern lives.
It just shows you even the most abstract ideas in math can have a huge impact on the real world. And in the case of prime numbers, well, their impact is everywhere in our digital age.
Okay, so we've talked about the history of trying to understand prime numbers, their weird connection to quantum physics, and how essential they are to modern cryptography. Feels like we've covered a lot, but I have this feeling there's still a lot more to explore.
You're right, we've barely scratched the surface. And you know what? Despite all the progress, that fundamental mystery of prime numbers, it's still there. The Riemann hypothesis, it's still a huge challenge for mathematicians, pushing them to understand these numbers even better.
I gotta say, even after everything we've talked about, it's hard to believe something so simple, a number that's only divisible by one in itself, could be at the heart of so many unsolved
I
mysteries.
know, right? That's the allure of prime numbers. They seem so straightforward, but they lead to these really deep questions about math, about the universe itself.
What about other unsolved problems, besides the Riemann hypothesis? What are some of the things that keep mathematicians up at night?
There are a lot, actually, but two of the most famous are the twin prime conjecture and Goldbach's conjecture.
Okay, lay 'em on me.
The twin prime conjecture, it basically asks, are there infinitely many pairs of prime numbers that are only two apart, like 11 and 13 or 17 and 19? You see these twin primes popping up all the time, but no one's been able to prove they go on forever.
That's wild. And what about Goldbach's conjecture?
Goldbach's conjecture, it states that every even number greater than 2 can be written as the sum of two prime numbers.
Okay.
So like 4 is 2 plus 2, 10 is 3 plus 7. Seems simple, right? And it's held true for every even number anyone's ever tested. But proving it's always true, well, that's another story. No one's been able to do it.
So even with all our fancy computers and math tools, these basic questions about prime numbers are still stumping us.
It's true. And it's actually kind of humbling. Shows us there's still so much we don't know about math. And the exciting part, We have no idea what amazing discoveries are waiting for us as we keep exploring.
It really is amazing to think about,
Yeah.
these simple questions about prime numbers, questions that really anyone can understand. They've stumped some of the greatest mathematicians for
The
centuries.
thing about math, isn't it? Even the simplest ideas, they can lead to these incredibly deep, complex mysteries. And with prime numbers, those mysteries, they seem to be tied to some of the most fundamental questions about, well, about the universe itself.
You know, Listening to you talk about all these unsolved problems, these conjectures, it makes me think about all the connections we've uncovered between different mathematical ideas. We started way back with the ancient Greeks and ended up talking about like quantum physics and modern cryptography.
It's true. It speaks to the unity of knowledge, often feels like there are all these separate fields of study, each with its own language, its own specialized knowledge. But when you step back, look at the big picture, you start to see these amazing connections, these underlying patterns that tie everything together. And prime numbers, they seem to be right at the heart of it all.
It's like we've been putting together this giant jigsaw puzzle, and prime numbers are some of the key pieces that hold the whole picture together.
A great analogy. And here's the thing, this journey of discovery, it's far from over. Given all the connections we've seen, who knows what other surprises prime numbers have in store for us?
Maybe the key to solving the Riemann hypothesis. It's out there, hiding in some field we haven't even thought of yet.
Exactly. Maybe the answer lies in quantum mechanics, or maybe it'll come from some brand new area of math, something we haven't even discovered yet. It's exciting to think about.
Makes you realize we're still just at the beginning of this exploration.
And that brings us to a final thought. What if, and this is just a thought experiment, but what if the key to cracking the Riemann hypothesis, and maybe all these other mathematical mysteries, it isn't about more calculations, more abstract theories. What if it's about a shift in perspective?
A shift in perspective, what do you mean?
Well, for centuries, we've been following in the footsteps of these mathematical giants, Gauss, Riemann, all the greats. And don't get me wrong, their work has been invaluable. But maybe, just maybe, their way of thinking, while brilliant, it's also limiting us.
So you're saying we might need to, like, break free from the traditional ways of looking at these problems?
I think so.
Hmm.
What if we need to develop new mathematical languages, new ways of visualizing these concepts to see the patterns that have been hidden from us all along?
That's a pretty radical idea. But yeah, I can see how it might be necessary. Like, we've been using the same map for centuries, and it's got us pretty far. But to reach those uncharted territories, maybe we need a new map, a new way of navigating this mathematical landscape.
Exactly. And that's the beauty of math. It's alive, it's evolving, always pushing the boundaries of knowledge. And prime numbers, well, they're going to be a big part of that journey, no doubt about it.
Well, I think we've done a pretty good job unpacking the mysteries of prime numbers today, or at least as good a job as anyone can with a subject this complex and fascinating.
We've explored a lot. The nature of primes, their history, their connection to quantum physics, cryptography, and of course all those unsolved mysteries that mathematicians are still grappling with.
It's been a real journey. I don't know about you, but I'm feeling a sense of awe, a sense of wonder, really.
And as we wrap up this deep dive, remember this. The search for knowledge, it never really ends. Keep exploring, keep asking questions, and keep being amazed by the world around us, because there's always something new to discover. And prime numbers, with their simple elegance, their profound implications, they're a perfect example of that.